master and PhD degrees in Washington University and University of California, Irvine, respectively. Then he had postdoc training at Boston University and MIT before starting up his own laboratory at Louisiana State University Health Science Center in New Orleans. Unfortunately, after the Hurricane Katrina, he moved his laboratory to the University of Maryland in Baltimore, and he continues his work over there as a full professor at the Department of Anatomy and Neurobiology. He has many publications in very prestigious journals. His main research area is the somatosensory system development and cellular and molecular mechanisms of axon target interactions and guidance mechanisms and synaptic plasticity. He is also co-founder of our summer neuroscience graduate schools, and he's a really loyal faculty member. We are very delighted to have him here today in Belgrade. And the title of his talk will be Somatosensory Circuit Alterations in Neurodevelopmental Disorders. Please, Dr. Erzurumlu.
Thank you, Max, and I'm grateful to the Serbian, Turkish, and Romanian Neuroscience Societies for inviting me here for this special FENS regional meeting. It's a pleasure to be in Belgrade. I am going to talk about the whisker barrel system of mouse. And this is a flattened brainstem cortical section of a mouse. And here you see the whisker representations and the entire body representation. This is equivalent to the human homunculus. This is the neurinculus. And this cartoon here is from a very old review I did with Peter Kine, and it just shows the mouse smelling barrels with his, or sniffing barrels with his whiskers. These whiskers are topographically represented in various brain structures all the way to the neocortex. And here's the body map, the lower lip, the forepaw, hind paw, and the whisker area. As you can see, about 1/4 or 1/3 of the entire body map is devoted to the whiskers. I'm going to tell you an anecdote. When I first started in neuroscience, there was no neuroscience departments anywhere in the world. It was either physiological psychology, neurobiology and biology departments, anatomy departments, physiology, pharmacology, biochemistry. There was a lot of neuroscience research, but there was no cohesive neuroscience. I came across neuroscience first at Washington University in St. Louis. At the time, I was quite fortunate because I had, as professors in various courses, Rita Levi-Montalcini, the discoverer of the neuron growth factor. I heard the story from her mouth. Victor Hamburger, Max Cowan, Ted Jones, a lot of people there. And one of the first courses I took there was a neurohistology course. And a young professor was leading that course named Tom Woolsey. He had started there as an assistant professor a few years earlier. And the first paper I read was about the mouse barrels. He had discovered the barrels and published a paper in 1970 in Brain Research. And that paper was the first neuroanatomy paper I read. And I did not know that the rest of my academic career I would be focusing on that. To me, it looked like a trivial paper. I couldn't really care much about the pattern formation of the mouse barrel cortex. At that time, there were more interesting things like the monkey brain, or even the cat brain, or the visual system. I didn't know that. Now, I'm going to share with you something for the first time, a public audience. This slide, nobody's seen it before except for the individuals present in it. These are the main players. I recently wrote a review paper on the barrel cortex with Dr. Gaspar, and it occurred to me to make a historical slide. I asked Tom Woolsey, here's Tom Woolsey. I asked Herb Clackey, and also Frank Rice to send me photographs of themselves at the time when they discovered the barrels. Tom Woolsey discovered the barrels and called them barrels along with Hendrik van der Loos, because he was a medical student and he was working in Hendrik van der Loos's lab during the summer, and he cut the mouse cortex in the tangential plane and did Nissl stain and observed these patterns, and he called them barrels. And he actually consulted all this with his father, Clinton Woolsey. Some of you may know his name. Clinton Woolsey is one of the pioneers of the human somatosensory motor cortices. He and Wilder Penfield discovered the homunculus, and he is Tom's father. And Clinton Woolsey initially was at Johns Hopkins, and later moved to Wisconsin. And Tom, when he went home to his father's, and worked more on his paper, and then published a paper. Now, you may be able to read this fine writing, but this is a quotation from Tom. This is a picture of him at the night of his wedding to his wife Cindy, right after he graduated from medical school. And this is the time, the day after he had submitted that paper, the classical barrel cortex paper to brain research. So this is what he looked like when he submitted the paper. Now, a few years later, there was Herb Plackey, my PhD advisor here, and he was a postdoc with Fort Ebner at Brown University. He cleverly picked up the Tom's barrel cortex paper, and he was using anterograde degeneration techniques, and he lesioned the ventroposteromedial nucleus in the thalamus, and using an anterograde degeneration technique, saw that in the cortex, thalamocortical axons form patterns too. So the barrels are formed by cellular aggregates, and thalamocortical terminals fill inside them. And his paper is also a classical one, and this photo is about the same time when he submitted that paper at his wedding to his wife Maureen, and both of them were Fort Ebner's tenants. They lived in a house, in a carriage house behind Fort's house. And in fact, Fort is in the background right here. This is a picture of Hendrik van der Loos when he moved to Lausanne soon after, and in 1976 he coined the term barreloids in the thalamus. And Frank Rice was a graduate student that overlapped with Tom, and Frank also moved to Lausanne, and he has his classical studies of describing barrels in different species, in rat, mouse, gerbil, hamster, etc. And here is Fort Ebner. This is a picture that I took. In fact, I was about to go to do a postdoc with Hendrik van der Loos years ago, when I was giving up my post at the University of Hacettepe in Ankara. Then I got an offer from Fort Ebner, and it was kind of an interesting idea for me to do a postdoc where my PhD advisor did a postdoc, so I chose Fort and went to his lab. Now, I don't know if you can see this writing here, this is an inscription. Years later, when I took my position at Louisiana State University, Mark Baer, who was also a graduate student of Fort Ebner, came for a visit. And while visiting my laboratory, he noticed that on one of the shelves there was a book, his textbook on neuroscience. And then I said, "Oh, I really like that book, would you sign it for me?" And this is an inscription he wrote in it. And says, "May your barrels always be full." Well, so this is the rest of my story. For 40 years or more, I have been working on this system. Now, in the early years, Hendrik van der Loos and his wife, what they did was they trimmed the whiskers, actually cauterized them, and saw that if you do that, the cortical patterns change. And for a very long time, we thought that periphery dictated the patterns in the cortex. Whether you did a lesion, also in Lausanne, Hendrik van der Loos and Egbert Welker, they raised mice that had extra whiskers, and they saw extra barrels. And here is an example that the Japanese group did. They ectopically expressed sonic hedgehog in whisker pad and ended up extra barrels. Now, in 2001, Tomomi Fukuchi Shimogori and Elizabeth Grove started doing these in vitro electroporations, electroporating various molecules or things into the mouse embryos. And when they moved FGF8 and the cortex would play, or when they ectopically expressed it, they saw that they could even duplicate barrel fields. Now, that sort of threw a lot of gas over a fire, because there was a huge argument going on that developed between the followers of Pashtorakish, that cortex was organizing itself. His idea was that there was a protomap in the cortex, and Denis O'Leary, who said cortex is a tabula rasa, and the cortical axons basically dictate how cortex is organized. Well, all of this brought the idea that both the periphery and the cortical intrinsic mechanism organize the brain, or organize the pattern formation. Now, the system, this paracortex or barrel patterns, come from the periphery. The trigeminal ganglion cells, their axons, connect to the whiskers, and then they convey this information to the brainstem trigeminal nuclei. And from there, the second order neurons send their axons to the opposite side, contralaterally to the thalamus, and from thalamus, the third order neurons now send their axons to the cortex, and they convey the template of the whiskers there. These are flattened embryonic brain stems that several of my past students are familiar with, and they work on, and the Özdinler and also the Mervolutumer. But here you can see the progression of the axons coming from the principal nucleus of the trigeminal, crossing the midline, and going towards the thalamus. So this pathway is contralateral. The left whiskers are represented on the right side, right whiskers on the left side. This is a really nice code, and that is one of my favorites. One of the most obscure issues in biology is no doubt to determine to what extent the organism benefits from the singular phenomenon of the depreciation. We don't really know what causes or what really makes some systems cross, but a lot of them do. Corpus callosum, anterior commissure, optic chiasm, and the descending motor pathway, it comes all the way to the medulla, and there the crosses, or ascending systems, they cross and go to the contralateral side. Now, what are the consequences of midline defects, midline crossing defects? There is a genesis or partial formation of the corpus callosum with cognitive deficits, or uncrossed and partially crossed descending motor tracts. In fact, a really curious example of this is in humans when this genetic defect occurs, when the right hand wants to do something, left hand copies it. If the individual is writing with the right hand, the left hand does the same movement, and they cannot help it because of the wiring of the system. In recent years, there's crossing, but also the most studied crossing defects have been in the visual system with the optic chiasm defects, such as albinism, chiasma, or Siamese cats. They all have crossing defects with altered retinal topic maps in the brain. In recent years, it's been shown that mutations in midline crossing gene, DCC or robos, have altered, for example, nociceptive topognosis. Humans with this defect, what happens is they feel a painful stimulus on one side, they feel it on both sides. So they cannot localize it to one side alone. So little is known about these midline crossing defects, especially along the somatosensory pathways. The only examples so far are this topognosis, the nociceptive topognosis with the DCC gene that's affected. For ROBO3 gene in the midline, they have the horizontal gaze palsy with progressive scoliosis. Now, just to briefly summarize the pathway coming from the whisker, the trigeminal ganglion, to the brainstem, and the principal sensory nucleus conveys to the contralateral thalamus, and from there to the cortex. This is the pathway, and these are called the barrelets in the brainstem, barrelloids, and the thalamus, and barrels in the cortex. In fact, Tom was the first one to call them barrels in the cortex. A few years later, Hendrik Wagner called them barrelloids, and in 1980, Tom called these barrelets. The names are funny, but they stuck around and they're used extensively now. Here is what the barrel cortex looks like with 5 rows of whisker representations in different stains. And there is a very curious mutation that I'm showing you here. And that is, the size of the face area or the barrel area is similar, except there are a lot of small and multiple barrels. And how does this happen? Normally, this is the 5 rows of whiskers that you see here that are represented in the cortex. And in this mouse, what happened is there is bilateral whisker representation, just like the visual system. The ipsilateral map is inserted into the contralateral map. And this happens not because there's something wrong in the periphery. The whiskers are normal, the brainstem patterns are normal, and everything in the cortex is normal. But what's happened is the pathway from the principal nucleus going to the thalamus got misrouted. So something went wrong in between. Up to this level, up to this mouse example, everything that was known was either something happened in the periphery or in the cortex that disrupted the pathway. This is the first example showing disruption in between the pathway. And when this happens, and this is because of a ROBO3 mutation in specifically neurons of the principal sensory nucleus, then we end up with an ipsilateral and a contralateral whisker representation in the thalamus and the cortex. Here you're looking at it with the glutamate transporter immunostaining from the brainstem. These patterns are normal, and the thalamus, they're ipsian bilateral or bilateral, and the cortex bilateral. How do we know this? We have done this by labeling with carbocyanine dyes, a green dye on one side, red dye on the other, and here, a normal animal, we have red only on one side coming from the opposite principal nucleus, and green on the other side. Whereas in these animals, the ipsilateral and the contralateral maps could be seen on both sides. Now, we can also prove this by doing selective whisker trimming and activation of a specific row of whiskers and looking at immediate early gene expression after activity, such as CFOS. Here's row C whiskers represented. There's a single whisker, C1 whisker, and you can also do arcs or different rows, etc. By doing all that, you can chart individual whiskers or which barrels represented which whiskers from both sides in a very precise manner. And here you see this again. The green is the ipsilateral in the robomouse, and the reds are the contralateral. The important thing is that the size of the barrel field is not different, but they're smaller barrels, and that they are both ipsilateral and contralateral, yet they're not overlapping. We've also done sensor dye imaging in the cortex, and usually with this imaging, when you stimulate one whisker, you get activation in the cortex in one spot, whereas in the mutant cortex, we have bilateral responses to C2 whisker stimulation. And the red here is just the ipsilateral and normal animal, and there's nothing with the blue of the contralateral stimulation, whereas in the mutant animals are both ipsi and counter representation. Now, how does this organization translate in terms of the individual elements? Normally, what happens is the barrel neurons, the initially described barrel neurons, they are organized around the barrel walls and orient their dendrites towards the barrel centers where thalamocortical axons form patches. And here, they seem to be disarrayed. And the layer 3 neurons, layer 2-3 neurons, which are above layer 4, that receive basically this information and distribute it across the cortical pathways, get this info. Now we've done some 2-photon calcium imaging layer 3, and we found that in the robo animals there are cells that respond bilaterally, which means that here now, in layer 3, we have cells that are convergent, that are getting convergent input from both ipsi and contralateral barrels, whiskers. Now, this sort of presents a peculiar case because up to this time, actually the initial report of barrel cortex or barrel mutation was one that I did with Susumu Tanagawa's lab years ago in the 1990s, when the first NMDA-R1 knockout mouse was generated, and there were no barrelette patterns in the brainstem. And later, I collaborated with another postdoc from Susunu's lab over for 20 years plus, and he generated cortex-specific, dominant-specific, and then the R1 or cyclase type 1, it's a mutant mice, and they all had paracortex phenotypes, either the cellular defect or the axonal defects. And not just us. Laboratories from around the world, whenever they had a mutant mouse, most people want to look at the barrel cortex as their phenotype. And a lot of them found specific phenotypes. For example, another one was if there's not there's a defect in release properties of thalamocortical axons, if they're not releasing properly glutamate, then the patterns won't form. Now, curious thing is, there are trends in science. Everybody's at that time really excited and saying, okay, we have a mutant mouse, let's see what the barrels look like. In fact, at one point my lab turned into a barrel testing station. Everybody would be calling, oh, I have this mutant mouse, can you check the barrels? Well, we didn't really think about the most important issues that's related to these phenotypes. The barrel cortex is not alone. It is not isolated and doesn't end there. It is connected to the rest of the brain, rest of the cortex. And now everybody's interest is shifting towards what happens downstream from barrel cortex. And here's where we start a new line of research, and that is, I'll only show you the cortical or callosal connections. Here you have the red whiskers on one side and blue whiskers on the other, just for identification. In normal animals, blue whiskers are represented on the opposite cortex, and red whiskers on the opposite. And when the cortical connections, the callosal connections form, they form homotypically. From around, they are located, these neurons, projection neurons are located around barrel septa, and they project to the equivalent region on the other side. And they use a lot of axon guidance molecules. So when you have a bifacial representation in the cortex, how does this affect the rest of it? This is a sort of a relatively new preparation that my technician developed, basically taking the entire hemisphere, both sides, and flattening it together after labeling. So you can see that if you do a labeling on one side, you can see all the projections in the entire cortical field. This is not as good a picture as the one I will show you next, but here you have an injection into the barrel cortex, and there's labeling. These are viral tracers and tertiary tracers with fluorescent labels. There's labeling in the S2 cortex, M1 cortex. There's labeling in the prefrontal cortex. There's labeling in the perirhinal cortex, all on the ipsilateral as well as the contralateral side. So if you look at the ipsilateral side, the callosal projections, the projections are homotypic. They go to only one position. Now, this is the preparation, and the way we do this is just to be precise, to localize the IPSI versus contra fields. We do intrinsic optical signal imaging after stimulation of the left or the right side of the face or the whisker, so we know where they're represented, and inject the viral tracer at that location. And then here, for example, this injection is in the contralateral barrel field of a robo knockout, condition knockout mouse. This is the ipsilateral map. And curiously, on the other side, the projections are both in the ipsilateral and contralateral side. If axonal connections follow intrinsic cortical programming mechanisms, they should be homotypic. But just because the contralateral barrel field and ipsilateral barrel field are side by side is really aberrant, the projections, what's happening is both the IPSI and the contralateral side are projecting to multiple zones on the opposite hemisphere. This, of course, is another example. That's an injection into the IPSI zone. This is on the contralateral side. This is the ipsilateral zone label and the contralateral barrel zone label. This is the reverse. That's a contra zone injection. There's the ipsilateral label and the contra label. Now, what happens as a result of this behavior? How do these animals behave? They do not show abnormal behaviors in terms of motor behavior or tactile sensory behavior on their paws. For example, if you put a piece of a sticky paper on the paw, normally mice sort of lick it off right away, and you just measure the latencies. If there's a problem of sensitivity, it will take them longer. If they don't sense it, they won't pick it up. Or if they're hypersensitive, they'll go at it right away. These mice are normal in that. The only effect that they show is related to whiskers. And one of the whisker tests is the gap jumping test. That's the only test that's known so far, or at least I know, that is specific to barrel cortex. And that was also developed while I was grabbing as a postdoc by Bruce Masterton. What they did was they cut off all the whiskers, left only one whisker alone, and then they sort of trained the rats to cross a gap using one whisker alone. The animal can detect the gap distance and then decide to jump or not jump. And if you lesion that particular whisker barrel, the animal couldn't perform the task. So that's the only task specific for whisker barrel cortex. And they do show deficits in that. They also show deficits in discrimination, not visual discrimination, but in the dark, tactile discrimination of objects with their whiskers. Now, a postdoc at the time, now an assistant professor in my group, Arakawa, developed a really interesting task, a new behavioral test. He built a platform, and on either side of the platform, there are pokes coming off. And the animal is placed on this platform, and it has to move along the platform towards the end. And as it's going, when it feels something on the right, it uses right whiskers to whisk at it. If it feels something on the left, uses the left whiskers to whisk at it. Normally, mice whisk the air freely, this exploratory whisking, but if they encounter something that they want to find out what it is, they do discriminatory whisking, which is high frequency. And these mice are showing rather peculiar behavior, turning their heads back and forth, and most of the time using their contralateral whiskers to detect the clothes. So basically, not just the whisker barrel cortex problems, its connectivity across all the way cortical connections have a major disruption when something goes wrong in the brain stem that's reflected in the thalamus cortex and in the whole perceptual work of the animal. Now I'm going to shift gears a little bit. Basically, what I told you is that these mouse mutations and examining the barrel cortex is revealing a lot of mechanisms of axon guidance and connectivity, circuit formation, and how that translates into behavior. But now I'll move into how some of the somatosensory circuit alterations are affected in neurodevelopmental disorders. Now, neurodevelopmental disorders are polygenic. They have a lot of genetic bases or relations, or they're not just because of a single cause, and a lot of different mutations or variations can cause a number of phenotypes. In all of these, in recent years, there's a term that's developing, it's called the tactile defensiveness, or tactile sensitivity. And hypo or hyper tactile sensitivity is a common characteristic in almost all of the neurodevelopmental disorders. And most of them is related to somatosensory system. And because of this, the mouse barrel cortex is also very useful because we know the morphology of it, we know the physiology of it. I've listed here a number of studies that have been pointing out how tactile sensitivity differences are prominent in various autism spectrum disorders and other neurodevelopmental disorders. Now, I'll talk to you about two mouse models, one associated with the Rett syndrome and the other associated with the autism spectrum disorders. As you all know, the Rett syndrome is related to the variations in the MECP2 gene, and this MECPG binding protein 2 plays as a transcription repressor or activator of many genes, and loss of function or overexpression is associated with several cognitive and behavioral disorders. And one of the genes regulated by MECP2 is MET, or c-MET proto-oncogene. And it's a MET protein is a receptor protein tyrosine kinase that binds hepatocyte growth factor, HGF. And both of them are expressed in the brain and play a role in neurogenesis, differentiation, migration, synaptic plasticity, and disruptions in net function have been identified as a risk factor for ASD. We have these lines of mice, a lot of them are commercially available. Either the MECP2 null mouse, since the MECP2 gene is X chromosome linked, if we get a deficient male mouse, which is a Y chromosome, then we call it a mutant mouse. Or we also have, using the LOX system, either the cortex-specific or thalamus-specific MECP2 or MET null mice. And I'll describe a little bit about the altered excitation inhibition balance using the thalamocortical device physiology approach. But before that, in MECP2 null mice, what happens is with ultrasensitive dye imaging, the same area or the specific area in the barrel cortex lights up after stimulation, but in the null mice, the area is very diffuse. This can be seen also with CFOS activation following viscous stimulation. The barrel patterns are there, but it's not as distinct or as clear as in a normal mouse. They're rather diffuse. Basically, the neurons in the layer 4 of these animals have characteristically regular spiking neurons, and they're not abnormalities in their spiking characteristics. And the stimulation of the thalamus leads to an EPSP-IPSP sequence. And when we look at the EPSP-IPSP magnitudes, normally EPSP are larger or equal to IPSP in normal mice, but in these animals, this EPSPs are smaller than IPSP, showing that there is an altered excitation inhibition balance and that there's more inhibition. Now, also when you do glutamate voltage clamp with the glutamate or GABA receptor reversal potentials, you can see that the problem is basically with the AMPA-GABA ratio, namely the excitation inhibition ratio is lower in these animals. Now, excitation inhibition can be lower because of either the convergence of inputs to a neuron, it gets less inputs, or more GABAergic inputs, or it could be related to release properties of the incoming inputs, or the response properties of the postsynaptic neurons. All of these, when we test it, appear normal. The only thing, I'm not going to go through them individually, the only thing that appears abnormal is that the GABA-A receptor amplitudes or IPSC amplitudes were higher. Basically, GABA-A receptors have, in the MECP2 null slices, the amplitudes of these GABA-A receptors higher, and that is because of that the excitation inhibition ratio is lower. Morphologically too, when we look at the thalamocortical axon terminals and the dendritic complexity of cells, there are differences, especially in the terminal tips. So these inputs are a bit weaker, but the main problem here is the GABA-A receptors. In contrast, in the MET-DMX1 mice, these are cortex-specific MET null mice. Again, basically all of the physiological features of the neurons are normal. The only thing is the average AMPA-GABA ratio, in other words, excitation inhibition ratio is now higher. And average amplitude of EPSCs are similar. The EPSCs have not changed, but mainly the problem is with IPSCs, but that meaning the GABA receptor, GABA-A receptor function is abnormal. As shown here, the amplitude of SIPCs are smaller. These are basically the traces. The amplitudes in normal animals are higher, and in mutant animals, the amplitudes of spontaneous inhibitory postsynaptic currents are lower. Now, in cortical and hippocampal neurons, insulin leads to increased surface expression of GABA-A receptors. And my colleague who did all these experiments tried insulin, application of insulin in slices, to see whether this would alter the excitation levels of the cells. And in fact, it did affect and lower the excitation level by adding insulin. But in the medinal cortex or medinal cells, the insulin alone had no effect. And that was kind of puzzling why this would happen. I mean, insulin increases SIPC amplitude but in normal animals, but not in med-deficient neurons. Fusanlo, who did these experiments, came up with the idea that how about if we sensitize the insulin, if we follow the insulin sensitization? Because insulin sensitization is used in diabetic patients. By insensitizing the insulin receptors, you can sort of normalize it. And one of the commonly used pharmaceutical agents for that is pioglitazone. It's a member of the iodine, I cannot pronounce this, PO. And this really helps the sensitizing both hepatocytes and also essentially neurons for insulin. And I'd like to point out, I have a bunch of references listed here. This drug is used recently in both Alzheimer's patients and also in ASD children. And there are some really positive effects coming up with these. So, in wild-type slices, when Fusan applied insulin, then the AMPA-GABA ratio got lowered significantly. But addition of pioglitazone to insulin did not make much of a difference. So here's the wild type with insulin and insulin plus PO, and it really doesn't make much of a difference. It increases the SIPCs, but it doesn't make any difference whether insulin is alone or with PO. Curiously, when this experiment was done in cortex-specific med-deficient animals, insulin had no effect alone, but when combined with PO, dramatically reduced the ratio. So the idea is that insulin sensitization can alter the excitation inhibition balance disorder, as seen in the thalamocortical slice of these medinal mice. And these are further verification of them. You can see the increase in SIPCs with insulin plus PO application, and here's the amplitudes quantified. And this is the cumulative fraction graph that shows it with insulin plus PO. This has moved to the right, so that it's really decreased it. So, basically, in conclusion, the in vitro electrophysiological studies indicate that there's an altered EI balance in the primary somatosensory cortex in favor of inhibition, meaning hyposensitivity in the mouse model of RTT, and in favor of excitation, hypersensitivity in the mouse model of autism spectrum disorders. Now, I'm going to make a major jump and speculate such that those of you who are familiar with Rett syndrome, a very typical phenotype of the syndrome in these Rett girls is that they do a lot of hand kneading and hand-to-mouth motions, playing with their mouth a lot or kneading their hands. These are very common, very typical. If you look at any photograph of a Rett child on Google or anywhere at the Rett Syndrome Foundation site, you will see this characteristic behavior in all of them. Well, think about the homunculus or the murinculus, the large area of the mouth representation and hand representation. This behavior has been, for a very long time, even now, has been considered as a stereotypical motor behavior. So a lot of mouse models of RTT, they do motor tests. These are called stereotypical motor behaviors. I submit to you that it's more than motor, it's somatosensory. Because of hypersensitivity, the individual with this hypersensitive state wants to stimulate those areas to reach a level of excitation. And that is really important. And conversely, in ASD children, in a lot of the cases, they are hypersensitive to tactile stimulation. That is, stitching in clothing bothers them, or seams in pants or other clothing bothers them. Everything that sort of feels on the skin they become aware of is problematic, and because of that, there are a lot of companies, clothing companies, that produce or that market clothing without seams, without laces, without anything that would bother the skin. And that is probably related to, again, I think, to hypersensitivity in the somatosensory cortex. And that could be perhaps alleviated by pharmacological means, I'm not sure. Now, tactile senses, if you think about it, unlike the other senses, is very important not only postnatally but prenatally. It's the first sense to develop in utero. An embryo needs to feel things, and as soon as the animal or the baby is born, they need the tactile sensation for suckling behavior, for close contact with the mother or parents, caretakers. And as the organism gets older or as the baby grows up, it also plays a major role in their development of own sense, body sense, where their body limits are. When you ask a little kid, where's your body, or when you show them a mirror, oftentimes they could be in a conflicting situation, but over time they will develop a sense of their own body and also a sense of the other person's body, where they are. So you restrict limits, or you initially set limits as to how close you can get to a person. You get close to a person if they're caretakers, or if you want to be hugged or loved by the ones you choose or not. And all of these play an important role as we grow up in social behavior or in emotional and personal behaviors. Not to mention the need to walk, the need to feel things, and I'm sure you're all familiar that babies recognize things by putting them to their mouths. Now, if there's an altered balance in the somatosensory system of all these, then these behaviors, not only tactile behaviors, but also the social behaviors will get affected. This is my take-home lesson. So in our studies, we sort of feel that application of insulin together with PO could alter the effects of this, sort of preempt the altered situation that's created by the hypersensitivity cases. And there are now studies that are coming up. In fact, there's a huge study in Canada that they called for volunteers last year or the year before to use the PO in ASD children and also placebo to compare them over time. So this is it, and I particularly use this barrels full of money or full of information. We've gained a lot of knowledge from studying this system, and also, including my laboratory, there are numerous laboratories, not in the US, but in Europe, in Japan, in China, who are getting funds for this research program. And I list here my collaborators from different parts of the world, and my research has been funded by the National Institute of Neurological Disorders and Stroke. Thank you for your attention.
If there are maybe just a couple of, actually, usually don't accept that. Yeah. Okay. Younger. Okay. Why don't you ask a question, because they usually don't accept, and there's a party, Neurovision party, so maybe we can accept one question from you about it.
Reha, wonderful, lifelong, almost lifelong devotion and a wonderful talk. Thank you. How would you comment on the relationship of insulin resistance in diabetes mellitus and peripheral neuropathy? I don't know whether the logic is the same or the converse.
This is against insulin sensitivity. This is against the resistance. This is trying to sensitize for insulin sensitization. So it sort of lowers the resistance. and makes both the hepatocytes and also in this case in the brain cells more sensitive to insulin when they are normally not. And the idea behind this was that these cells may have lost insulin sensitivity, like they're almost like diabetic neurons. And perhaps with the addition of this insulin sensitization, they could be normalized. For peripheral neuropathy, I have no clue how that would work, but that sort of brings an interesting but a note that a couple of years ago, David Kinty's group published a paper in Cell, and they looked at all these mice that I described, and their claim was that all of this is happening in the periphery. The peripheral neurons or sensory neurons have problems or issues in communicating the excitatory impulse to the somatosensory system, and that's where there's altered sensitivities. However, we got really clear evidence for the cortical cells, at least in a dish, and we know that it happens in the cortex if there's an altered balance. That could not come directly from the peripheral transmission of peripheral issues because it's related to GABA-A receptors. It's a receptor surface recruiting or receptor expression in the cortex. In other laboratories, for example, that are working on visual system and auditory system, they're also finding similar types of altered excitation inhibition balance. In fact, the first excitation inhibition balance issue was noted in the hippocampus and in the motor cortex. There are 5 neurons of MECP2 non-mice. So they're not just unique to somatosensory cortex, they're all other places as well. And this balance is really important and could be changed by pharmacological means. And I don't know how effective that will be in vivo conditions.
As far as neuropathic pain, pathological pain, plasticity. Yeah.
Okay, I would like to thank Dr. Erzurumlu for this wonderful lecture and also sharing those private photographs and memories with us. And also to the audience and participants, thank you so much. I guess we can close today's session and also the day and have fun at the Neurovision party then. Yeah.